For the first time in human history, scientists have peered deeper into the sun than ever before, revealing hidden layers, strange movements, and clues about the future of our star. This isn't about pretty images from telescopes. It's about cracking open the sun's internal heartbeat using helioseismology, solar wind sensors, and high-energy particle data from missions like Parker Solar Probe. These discoveries are reshaping how we understand solar storms, magnetic fields, and the long-term evolution of our star. In this video, we break down what researchers actually found, why it changes previous models, and how it could improve predictions here on Earth. For decades, scientists thought the sun's core was essentially hidden, forever sealed behind layers of plasma too dense and bright to penetrate. That changed thanks to a combination of tools that don't see light, but instead track the sun's vibrations, particles, and magnetic fingerprints. Helioseismology, for instance, measures sound waves generated inside the sun. These waves ripple through the entire star, revealing density changes, temperature gradients, and rotation patterns. Recent improvements in frequency sampling produced the clearest core signals ever recorded. Meanwhile, Parker Solar Probe has been flying closer to the sun than any spacecraft in history, collecting solar wind particles that carry information from deep magnetic structures. These particles show how waves travel outward from the sun's interior, helping researchers map processes that start far beneath the surface. Add neutrino measurements, tiny particles created during fusion, and scientists now have a triangulated view of what's happening at the sun's center. Together, these methods offer a new level of detail, sharper boundaries for the radiative zone, clearer energy transfer patterns, and stronger evidence of subtle mixing inside the core. This foundation sets the stage for what scientists uncovered next: insights that challenge long-held assumptions about the sun's internal behavior. The new findings reveal that the sun's internal structure is not the smooth, uniform sphere older textbooks described. One of the most surprising results is evidence that the solar core rotates more slowly than predicted. Earlier models suggested the core might spin faster due to leftover angular momentum from the sun's formation. Instead, new frequency splits and oscillation data show a calmer, more stable rotation rate. This changes how scientists calculate energy transport and magnetic field generation. Another breakthrough involves the Tachocline, the thin, turbulent boundary between the radiative and convective zones. Improved mapping shows this region is more sharply defined than believed, acting like a magnetic shear engine. This layer is crucial because it shapes the solar dynamo, the process that drives the sun's 11-year solar cycle. Researchers also detected signs of asymmetry in fusion byproducts, suggesting the core doesn't mix as evenly as once assumed. This uneven distribution has small but important effects on solar brightness, cycle timing, and even the sun's future lifetime estimates. These internal features create a more dynamic picture of the sun than ever before, and they have very real consequences for life on Earth. So why do these deep interior discoveries matter beyond the world of astrophysics? First, they dramatically improve solar storm forecasting. Space weather affects everything from satellite navigation and aviation routes to communication networks and astronaut safety. If the sun's magnetic fields form differently than expected, the timing and strength of eruptions can shift. Better interior models mean we can understand and predict those changes before they reach Earth. Second, these findings refine long-term energy output predictions. Even subtle changes in the sun's internal structure can influence climate modeling. This doesn't mean sudden climate swings, but improved accuracy for long-range studies that depend on solar variability. Third, understanding our sun helps scientists model hundreds of sun-like stars studied by telescopes like JWST. That means better exoplanet habitability estimates, improved age measurements, and clearer insights into how solar systems evolve. In short, learning what's happening inside our own star boosts our ability to understand countless others. These breakthroughs also guide future missions, especially the final close passes of Parker Solar Probe, which will skim just above the sun's surface. The better we understand the inside, the better we can interpret every burst of data coming from those extreme flybys. The sun is no longer a mysterious glowing sphere with an inaccessible heart. With new tools that read vibrations, particles, and magnetic waves, scientists are finally decoding what's happening deep beneath the surface. These insights reshape our understanding of solar activity, help protect satellites and power grids, refine climate predictions, and unlock secrets about stars across the galaxy. We're entering the first era where humanity can truly read the sun from the inside out. If you enjoyed this breakdown and want more space science explorations, make sure to like, share, and subscribe, and check out more deep space stories on our channel.